Hello everyone, welcome to the webinar, Condition Monitoring, How Sensors Are Enabling Industry 4.0, brought to you by TE Connectivity. I'm Lee Teschler and I'll be your moderator today. Just a couple of housekeeping details before we get started. You'll see several boxes on your desktop, all of which can be moved around and resized to suit your preferences. You can enter your questions in the Q&A box, and they will be addressed after the presentation. Another box to note is the Additional Resources box. This box has websites and other information on the subject, and we also have a tweet box right on the desktop, so feel free to tweet any interesting points right from there. And there's a list of hashtags for you to use. Now let's meet today's speakers. John Tuley is the Senior Manager of Business Development for Sensors at TE Connectivity. John has been with TE since 2010. He holds a BSEE from the University of Texas at Austin and an MBA from Baker University. Devin Brock is TE's Manager for Sensors Product Knowledge and Training. He has an electrical and computer engineering degree from Clarkson University and has over 25 years of sensor-related experience. Richard Brown began working with sensors and actuators in 1984 and has remained focused on applications of transducer technology throughout his career. Richard has authored numerous patent applications, conference, and journal papers. He provides application support within the EMEA region for a range of TE Connectivity sensor product lines, including piezo film vibration, force and torque, ultrasonic, and optoelectronic components. And with that, I'm going to hand things over to our speakers. Here you go, guys.
Thank you, Lee, and thank you for Design World for hosting this webinar. And for all the listeners, really appreciate you taking time to listen to us on this seminar. And please ask questions. There will be a comment box on your screen, so please ask questions and we will answer them after the presentation. In today's webinar, we're going to cover four main topics. The first one is really around definitions of condition monitoring, as well as some of the trends that we're seeing on the sensor side, as well as in the IoT space that's really enabling the market to see the growth that's been planned and discussed over the last several years. We're going to talk in detail around vibration and how that's implemented in some factories and some of the data that comes from vibration sensors. And we're also going to review some of the TE sensors that we have out there, and specifically around some of our wireless technologies around Bluetooth and LoRa for industrial sensors for industrial condition monitoring applications. And then at the very end, we're going to review a few use cases that really highlight how some of these sensors are used in real-world applications. Let's start with some basic definitions first. And I wanted to highlight this because you hear the terms a lot of Industry 4.0, condition monitoring, IIoT, the digital factory. All of those terms are used interchangeably. And depending on the audience, depending on who you're talking to, people will throw out different terms at different times. So how we look at it is, and by the way, the Industry 4.0 definition is from the Wikipedia definition out there, but really the Industry 4.0 was really started by the German government and coined as a way to describe the next advancements in factory automation and maintenance, really tying all of the machines together in machine-to-machine connectivity, IoT cloud-based platforms, software subsystems, et cetera, to really tie all of these assets in a factory together to be able to connect and leverage big data. So that's the overall superset of, all of the terms that you hear. Condition monitoring is a subset of this Industry 4.0 initiative. And what condition monitoring is really where we're trying to get sensors, and get equipment and really start to try to monitor and do continuous monitoring on these machines so you can start trying to predict when they're going to fail. And that is really important for factories to improve uptime and other things, and I'll show that on the next slide. As discussed earlier, there is high value in adding condition monitoring to factory assets and also any discrete asset, pumps, motors, things like that as well. But the real critical point is that if you're going down this path, you really need to understand what the value proposition is and clearly articulate this to who the stakeholders are. And that can be if you're a customer trying to implement this, leveraging components or devices and platforms out there, or it can be a company who is actually putting that platform together for an end user. Really need to articulate that to the end user what the value is. And here's some of the examples. It's high value because it can allow you to predict when these assets are going to fail and give you more data, having continuous monitoring. So as you're continuously monitoring all these devices, you can start to trend it and see when things are changing so that you can react quicker instead of having the machine fail and then either cause a delivery issue or unexpected downtime. Or in some cases, it allows you to not have to inventory as many assets. So you don't have to have, 3 or 4 spare parts available for that machine. You can order them as they come in. So those are some of the values, but it really all boils down to how do you reduce your operating expenses when you implement a condition monitoring, or how you are able to improve your customer service, improve safety, improve compliance, all around those type of areas. Now, this is a little history on condition monitoring. And if you look at it in the old days, if you've been around factories a lot, you'll know that guy. And by that guy, I mean somebody who's usually a maintenance manager that would walk around the factory, and he could literally, or she could put their ear up to a machine and just listen to the machine and go, wow, I think this one needs to be repaired, get his crew on there, and they'd go repair it without really having to, tear it apart or do any big analytics. It was just that gut feel type of approach. And back in the days, these guys were absolutely reliable, or actually they were invaluable to the plant reliability. And typically there was 1 or 2 of these guys in a big operation. So now what's happening is what we're trying to do with condition monitoring and predictive maintenance is how do you duplicate, that guy walking around your plant to be able to really listen to all the machines and continually know when these things are going to fail. So that's what you're trying to do with condition monitoring. And the other thing I hear a lot is, hey, this has been around a long time with PLCs and SCADA systems, and we've been putting electronics on it since the 70s. And yes, there has been a lot of electronics, a lot of more intelligence around machines, but they've really leveraged around the diagnostic capabilities of being able to say, hey, this failed or that failed or this on a machine. And what's happening is now we're moving to this whole idea where we can start prescribing the solution and saying, wow, this machine is starting to act a little funny. It's giving some data on vibration. It's changing pressure readings, whatever sensors you have on there. And now it's time to be able to do something different, and you need to go check this machine before it fails. And then in the future, and this is where you hear a lot of the discussions around AI and machine learning, is how do you get really more smarts in there with a cognitive approach where you can go into the machine and the data will tell you not only, hey, your machine's going to fail, but it'll say your machine's going to fail, next week, and by the way, you're going to need to change these seals or these bearings, and that's where your failure mode is going to be. So this is really exciting to see the progression, and as AI improves, I think we're going to see us getting to that point where machines are going to be able to self-diagnose and really understand and tell you, hey, I'm going bad and I need to be able to need XYZ repaired. So this is very exciting times for the condition monitoring space. Now here are some of the trends that we're seeing in condition monitoring that are really driving this adoption. I'm going to start in the upper right around low power wireless. So being able to connect, low power wireless sensors to assets and add sensing capability there really lets you both expand to the balance of plant assets. It lets you go into remote locations that are very expensive to run wires and power. So it really gives you flexibility. And I'll talk about some of the trends in the sensors side of the world, but low power wireless is a key enabling technology. The second one is advancements in analytics and edge computing. I'm sure everybody's read a lot about the edge compute and analytics companies out there. But these algorithms are getting a lot more sophisticated and are able to run on smaller and smaller platforms. So, and that is driving bigger, the ability to implement this in more locations. Network communications, we're seeing the cost of network communication drop significantly, especially for cell. Even satellite is becoming much more reasonable now. And then you have the whole range of ISM band private networks that you can go develop as well. And then I talked about a little bit on the previous slide of being able to implement continuous monitoring versus spot monitoring. That's a game changer because all that data goes into these cloud analytics platforms and gives them the raw data they need to be able to, to predict and start doing that cognitive analysis on the machines. And then the top two are really data anywhere, anytime. All these cloud platforms. I mean, there's very many cloud platforms out there. And then the need for visualization and being able to monitor assets anywhere, anytime, especially very timely with COVID and all the issues there. We absolutely, have seen a demand for more people wanting to implement some type of, remote monitoring and remote data and analysis. So the sensor trends are really enabling the expansion of IoT. And I always like to say that the sensors are the foundation of an IoT system. If you do not have good sensor data, you will not have good data that goes in for your analytics engines, your AI, your machine learning. So the sensors are absolutely a critical piece of that. And the trends that we're seeing really are very closely aligned to making and supporting this expansion of sensors out there in condition monitoring applications. It really resolves about miniature, smaller size, digital outputs so they're easily connectable to microcontrollers, sensor fusion where we're putting multiple sensors in the same package so you get the advantages of size, space savings, lower power devices. That drives the wireless connectivity, so you can now have wireless sensors that last, 4 years, 5 years out there, very common, some even up to 10, depending on your communication frequency on that. And then the last one is really around packaging and making sure that these things are packaged in for harsh environments, as well as getting the right certifications to be used in oil and gas and chemicals, factory floors, things like that, so that the parts will stand up and you will get your reliable data for a very long time to support your analytics and give you the data you need for condition monitoring. And with that, I'd like to turn it over to Devin.
Thanks, John. We thought it would be helpful to cover some of the key applications for condition monitoring, as they cover a broad range of industrial and commercial markets. Some of the significant areas include pumps, motors, and other machinery in the industrial and oil and gas markets. Commercial building monitoring and HVAC systems is another key area where companies are looking to increase the efficiency and uptime for equipment while ensuring that workers are in a safe and productive environment. Hydraulic applications, as well as wind turbines and other power generation equipment, is another growing area for condition monitoring. Additionally, monitoring and control of fluids for industrial and agricultural applications, along with equipment used for manufacturing and production, such as conveyor systems, rounds out some of the key focus areas for condition monitoring. The application areas for condition monitoring are varied and growing, and these applications rely on a variety of sensing technologies to provide the critical process data needed to make key decisions that affect everything from manufacturing efficiency to uptime and preventative maintenance, as well as employee safety and productivity. Sensor technologies in condition monitoring include both wired and wireless sensors and cover all the important process parameters companies need for their business. While the key technologies include vibration, pressure, and temperature, they can also encompass other technologies from position, speed, humidity, and fluid property, as well as others. TE Connectivity designs and manufactures an extensive range of industrial sensors from surface mount and board mount components to rugged wireless transducers with sophisticated electronics and edge computing. To discuss some of TE Sensors' key products in the condition monitoring market, as well as some features that set them apart, is Richard Brown, one of our field application engineers in the EMEA market.
Thanks, Devin. So as we've mentioned, one key element of most condition monitoring is vibration. What do we mean by vibration? Vibration is simply excess or unwanted motion. We can monitor the motion of a structure by looking at its displacement, or its velocity, or its acceleration. For reasons I'll come to shortly, we most often want to measure acceleration, and we do this with a type of sensor known as an accelerometer. An accelerometer converts mechanical vibration into an electrical output signal, and on this slide, the upper two traces show plots of voltage versus time. On the left, the blue trace represents the signal from a machine in reasonably good condition. On the right, the orange trace shows the signal from the same machine, but in relatively poor condition, with a variety of mechanical issues. To investigate these signals in more detail, we need to look in the frequency domain, and we do this using a mathematical process known as the fast Fourier transform, or FFT. This algorithm breaks down a time signal into its frequency components, and we can show these now as a plot of magnitude versus frequency. A narrow vertical line in the spectrum corresponds to a pure sinusoidal tone in the time domain. And we can see on the left-hand blue plots that relatively smooth time signal contains just 4 frequency components, or tones. On the right-hand plot, there are some changes in magnitude of the original tones, but there are also many new tones that weren't there before. Here we overlay the blue and orange plots from before, and we can begin to interpret some of the frequency components in terms of their mechanical origin. Machines typically run somewhere between 600 and 3600 RPM, and this translates to a frequency band in 10 to 60 hertz. If there's imbalance in the machine, this will typically show up at the running speed. Misalignment usually shows at twice the running speed, and normal bearing signals at a multiple of several times. Gear train signals are typically even higher multiples of the running frequency. So that's the blue trace in good condition. When wear occurs, we often see modulation effects or sidebands appearing around the bearing and the gear frequencies. Damage to bearings or gear teeth tends to be associated with discontinuities in displacement. And because acceleration is the second derivative of displacement, this results in a whole families of higher harmonic components and a general increase in the high frequency noise in the acceleration domain. This is why accelerometers are particularly useful in condition monitoring. The early detection of these changes in the high frequency signals is key to predictive maintenance. With some prior knowledge of the machine, we can assess the extent of the wear or the type of defects occurring and predict when maintenance should be scheduled. On the previous slides, we showed the spectral plots as log magnitude versus log frequency. Why? Well, here's what we see if we use linear scales for both X and Y. The lower frequency signals are kind of huddled up towards the left-hand side. The presence of the high frequency harmonics for the machine in bad condition can barely be seen. These components can be a 40 dB down or a factor of 100 less than the running speed component. Logarithmic scaling lets us see the details that would otherwise be very difficult to resolve. This also shows why we need a high dynamic range and a very low noise floor from an accelerometer for condition monitoring. We've talked about using an accelerometer for vibration monitoring, but how does an accelerometer actually work? Here's a cross-section of a typical packaged plug-and-play component. There's a central support pillar, a cylindrical piezoelectric sensing element, and around that there's a concentric inertial mass. If we shake this structure up and down in the vertical plane, inertial force exerts shear stress on the piezo element, and we see the electrical response to this. If we shake it in the horizontal plane, we get no output at all. Many of our accelerometers for condition monitoring are built using this general construction. Some of the smaller board mount components have different internal geometry, but still rely on inertial forces exerted on a piezoelectric crystal. Why do we prefer piezoelectric technology for condition monitoring accelerometers? We can easily achieve an operating bandwidth of over 10 kilohertz. We also obtain a very low electrical noise floor, particularly at high frequencies. The piezo sensing element requires no excitation signal. It's actually a source of charge or voltage. Therefore, piezoelectric accelerometers can operate using very low current or power. This makes them ideal for battery-powered systems. Finally, the sensing elements are very stable and don't change in properties over time. And this is critical when tracking changes in signal amplitude over the lifetime of a machine. So here's an example of a product we've designed specifically for condition monitoring. It's our wireless accelerometer, Model 8911, using the LoRaWAN network protocol. It goes without saying, if you have many machines in a plant, you perhaps want to monitor several locations within each machine or along a production line, then using wired sensors can quickly become an issue. But using wireless, a single gateway can handle hundreds of sensors, and the installation becomes much simpler. We've talked about the need for broad bandwidth to detect signals for condition monitoring, but it's generally not practical to stream data continuously from a battery-powered device. The LoRaWAN protocol itself doesn't support high data rates, so instead, we've put some edge computing into this sensor. First, we compute the FFT of the time signal, just like we showed before. And then we extract key features from the FFT result. We identify the frequency, the magnitude of the strongest 8 peaks, along with the fraction of total energy that each peak represents. This compact summary of the data then forms the uplink payload, which is transmitted once per period. The user can select the transmit interval between once per minute and once per day. With very infrequent uplinks, we can achieve a battery life of up to 10 years. This way, we're sending just 48 bytes per uplink and not transmitting 48 kilobytes per second of raw data. The 8911 also measures and sends temperature information. We're showing here an example spectrum with identified peaks, a block diagram of the internal function, and an example of the LoRaWAN uplink payload. So we've talked about our wireless model 8911, but I also mentioned earlier we offer components for board mounting. Our piezoelectric embedded accelerometers include the Model 820M1, which is designed for full reflow surface mounting, gives a 10 kilohertz bandwidth, and takes just 62 microamp supply current. Our Model 832M1 offers similar performance, but in a triaxial configuration. And when a wired solution is preferred for whatever reason, we do have a range of devices packaged for industrial use, such as our low-cost Model 8711, offering IEPE constant current output in a hermetically sealed IP67 stainless steel package. So we've talked about condition monitoring using accelerometers to measure vibration, and that's a very important aspect, but it's not the only approach. Machine condition can also be critically dependent upon lubrication, and oil condition can certainly degrade over time. To monitor oil condition, our FPS 2800 fluid property sensor measures 4 parameters simultaneously: dynamic viscosity, density, dielectric constant, and temperature. By measuring these parameters, the user can monitor subtle changes in condition occurring over time. These changes can result from oxidation, running a machine at high temperatures, or through contamination from water or other fluids, or from metal particle buildup due to mechanical wear and corrosion. And again, with some prior knowledge of the oil, we can look at where the oil is within its life cycle, thus enabling predictive maintenance. This is a fully integrated digital device with onboard microprocessor communicating over a CAN bus, packaged for harsh environment factory calibrated and with excellent long-term stability. So here's an example of what happens to 15W40 oil after 1,000 hours of use in a combustion engine. Blue traces are before, red traces are after. Oil viscosity only changes slightly, and it's more of a shifting gradient as a function of temperature. But density and dielectric constant show much larger changes, and these are distinct at any measurement temperature. So once again, by continuous or frequent measurement, we can resolve small changes in condition, and this can enable predictive maintenance. And even after the maintenance is done, the FBS 2800 can check whether the right type of oil was used. And with that, I'll hand back over to Devin for some further product overview.
Thanks, Richard. TE has one of the broadest portfolios of pressure sensing products, including a range of board mount sensors, as well as rugged transducer products. With the recent acquisitions of Silicon Microstructures and First Sensor, TE has expanded their line of pressure products to better address the low and ultra-low pressure applications. On the transducer side, two wireless products use the latest BLE communication protocol to transmit data, while the wired product range includes both analog and digital products for sensing caustic media and a range of sensors for hazardous locations, including products that have been certified as explosion-proof, intrinsically safe, or non-incentive. TE also provides a range of transducers specifically for submersible applications for level monitoring. On the temperature side, TE's temperature portfolio includes 5 different technologies, including NTC thermistors, RTDs, thermocouples, thermopowers, and digital temperature sensors. TE's broad portfolio of temperature probes are designed specifically for a range of industrial condition monitoring applications, including sensors for stator windings, bearings, and surface temperature sensing. Standard and customized designs include RTDs, thermocouples, and NTC thermistor sensing elements in a wide range of mounting configurations, wire insulation, and connector options. TE also provides a range of components, including thermopile elements and modules, in a family of digital temperature sensors. TE's products on the humidity side include both surface mount sensors as well as rugged probes that can accurately monitor both humidity and temperature over a wide range of operating temperatures and from 0 to 100% relative humidity. Designs include both analog and digital versions suitable for a range of condition monitoring applications. There are several manufacturing processes where monitoring and controlling humidity is critical for both efficiency and quality, including many painting, coating, and printing processes. Additionally, from an employee standpoint, the monitoring and control of humidity and temperature in the production facility has been shown to improve the productivity as well as the health of workers. TE Sensor manufactures speed sensors with 3 different types of technologies, including Hall effect, variable reluctance, and eddy current products. These speed sensors can operate over a wide temperature range and are suitable for frequencies from 0 to 20 kilohertz. Multi-channel sensors are available that allow for monitoring multiple systems for redundancy or to implement self-diagnostic capabilities. TE can also provide the corresponding pole bands that are used as targets for the speed sensor, as well as tachometers and other instrumentation. The speed sensors can be used for speed feedback and control, and can also be used to detect bearing wear and resonant vibration as part of a total machine health monitoring system. Speed sensors are found in a variety of condition monitoring applications, including power generation equipment, hydraulic motors, and to monitor wind turbine blades for both speed and direction. Speed sensors are applicable to any piece of rotating equipment where the monitoring and control of the speed of rotation is important. Finally, TE's position sensing technologies include a range of linear variable differential transformer, or LVDT sensors, which are suitable for detecting very small linear displacements in very demanding applications. TE also has a range of anisotropic magnetoresistive, or AMR sensors. They're well suited for noisy, dirty industrial environments and provide reliable, accurate, non-contact position feedback for both rotary and linear position sensing. Other position technologies that TE can provide for condition monitoring applications include cable extension sensors, sometimes known as string pots, as well as a wide range of precision potentiometer products. Key applications include everything from valves and actuators to servo motors to building dampers controls. Now back to you, John, to discuss some real-world use cases.
Thank you, Devin. I wanted to highlight two use cases here for everybody. The first one is one that we used inside our plant, and in the picture you see there is actually on an extractor motor in our factory in Toulouse. That is a LoRa 8911 wireless accelerometer that you heard about earlier, and that is connected through a gateway that is on the top of our factory in the building. And we basically took data from this vibration sensor over a period of a year, and what we saw over time is that two things really started seeing to start predict failures. One of them was the fact we saw the noise floor start to go up, and then we started to see those very high frequency spikes of transients come out on the sensor, and that really was a signal that the motor bearings were starting to go bad and we had to go do maintenance on the engine. So it actually showcased inside our own factory how those sensors can be used to detect failures and faults. The second application is with one of our partners called MachFu. They're at machfu.com. And this is an agricultural water solution. And this one is using both our vibration sensors as well as our Bluetooth-enabled pressure sensors. And you can see the different places that these are used on the tanks, on the wellheads, on the motors out there, the pumps, so that you can see how those are connected, and then they all go through to the gateway either via LoRa or Bluetooth, and then they're sent out over a 485 to the customer's monitoring system that way. But that could also be through LTE or any other way backhaul may. But this is a real-life example that was implemented for a customer to go off and monitor assets in a farm field to make sure that the irrigation, there was no leakage, that it was irrigating correctly, the right amount of water, the right amount of pressure, et cetera, et cetera. And by the way, this also helps with regulatory issues in some of the states that have water limitations and restrictions. So I hope these are helpful for everybody just to kind of see what we've done with these things in real life applications. Thank you for everybody spending time on this webinar today. And if you need more information, please reach out to us at www.te.com, which is our corporate webpage, as well as we have a specific dedicated IoT support email address, which is iotsupport@te.com. Would love to hear your questions and your projects that you're working on in any way that we can help. So thank you very much. And with that, we'll go back to the moderator and some questions.
Okay, thanks for that, guys. We've had some questions come in while we were talking, so why don't we get right to those. First one concerns sensors that transmit their status back. When you have that, what's the frequency of transmission that will allow 10-year battery life? Like suppose you had to transmit every 4 hours or so, how long do you think the battery would last? And have you ever considered vibration energy harvesting to kind of increase the life of the power supply? Somebody want to tackle that one?
Yeah, I'll take that.
Yeah, this is
John
Richard
here. And, okay, Richard, you want to take it? Go ahead.
Well, I was certainly on the battery life. I can give a rough kind of example. If it was transmission once every 4 hours, say this does depend on the spread factor of the LoRa system, how close the transducer is to the gateway and other factors. But typically, I would say theoretically in the range of 6.5 to 9 years. So if the spread factor is low, if it's SF7, you should get around about 9-year battery life
from the 8911. In that range. So for once per hour, should be 5 years, roughly speaking.
Yeah.
Good question. For vibration energy harvesting, we've looked at vibration energy harvesting over the years. We're not there yet. It's interesting, but in terms of the type of vibration spectrum and the amplitude levels that come in from a lot of condition monitoring, the energy level I just don't think is there yet to sustain charging of a rechargeable cell, for example.
I see. Another question for you on that case history you mentioned. Can you tell us a little bit more about the engine of the machine that was being monitored?
I can take that, Richard. So basically, it's an extraction motor inside of our factory, and honestly, I don't know the actual horsepower and size of the motor. You can kind of see in the picture on the presentation. There's the size of the motor, but I can find that detail out if you need us to.
Okay. Another question about that battery life, that 10-year battery life you guys mentioned. What size battery are you talking about for that estimate?
It's a CR123.
Okay. Okay. Another question. How do you figure out the optimal location for sensors when you've got an application? What goes into that decision process?
Well, I think this will be that's always the $1 million question on these on putting the sensors in, is where do you put them, and then also how close do you need your gateways and all of that type of thing, right? So I think I hate to say it this way, but it's more application dependent. So the farther you can get away from any interference is the best. But the reality of it is, when you put them into factory environments, you have a lot of metal, a lot of stuff in the way. So you really, have to, it's really case by case. I don't know if anybody else has a better answer, Richard or Devin. I don't know if either one of you guys have a better idea on that or how to answer that.
Yeah, I think sensor placement on the machine itself, if that were the question. I mean, what is a typical machine? I mean, the good thing is vibration does couple extremely well through most structures, so you can be surprisingly remote from the source and still pick it up. But the closer you can get the sensor to the actual source of the noise itself, the better. But I think it's hard to answer generically.
Yeah, and I was thinking more on the wireless side, to be able to connect in wireless. So you answered on the application side on the motor, and I was answering on the wireless side. So you got both answers there.
Hey, John, I can add a little bit to that, too. Our 8911 accelerometer has a magnetic mounting feature. That's one of the options for mounting. And that gives the user the freedom to experiment by placing the sensor in various locations on the machine or the motor and experiment to see where he gets the optimum signals and optimum response that he's looking for from the accelerometer. And it makes it very easy to do. As I said, it's just a magnet, and you can put it anywhere.
Okay, great. Another question for you. A lot of times the sensor data, you're trying to get it up to a cloud somehow. Do you guys offer gateways to do that, or how do you make that connection?
Yeah, what we do is, what we can do is we can recommend partners that we've worked with in the past that have connected our parts via the gateway. So pretty much, for the LoRaWAN spec on the 8911, that will connect via any LoRaWAN certified gateway. And then for our Bluetooth product, it's a standard Bluetooth protocol, so it's pretty straightforward to connect. But if you want some recommendations, we can absolutely give that if you reach out to us.
what's the range of a low rate of communication link? We talking feet, tens of feet, hundreds of feet, miles, what?
It all depends. If you're in open air out in a field in the middle of a farm field, you're probably talking, 10 kilometers in that range. Very low data rates, remember, but it's very long distance. When you're actually in a factory, to give you an example, that same application in our Toulouse facility, it's a multi-site factory. We have one gateway on the top of the building, and that gateway communicates throughout all of our different factories. So you're effectively getting a good, kind of 1 kilometer circle in a range pretty easily that way in that application. But again, this is where you really need to play with it a little bit to understand, how far the range is going to be. But one trick, though, is get the gateway as high as possible. The higher, if you can put your gateway, we've had customers that have put them and tried ground floor to third floor, and it makes a huge difference in range and the ability to communicate, having them up high.
Okay. Next one is about intelligent sensors. Seems like the sensors you got now are kind of intelligent compared to previous generations, but exactly what's the difference between an intelligent sensor and that's you might find present day and what you might see coming down the pike?
Okay. Why don't you start, Richard, and then I can chime in after you. That'll be the best way.
I was just going to say we're starting off where we are doing, for example, in the Model 8911, where we showed that we were FFT processing the time signal, and then after that extracting key features out of that FFT to send the useful data, the data that actually shows changes. And of course we're looking to expand into more detailed machine learning type applications in future, and just exploring how the functionality of the sensors can still be further enhanced.
Yeah, and we're working with quite a few different analytics companies, and what we're seeing is the machine learning is starting to be pushed down lower and lower into the device level and being able to support on smaller cores. So I think long term, I think you're going to start seeing a lot more intelligence around machine learning and AI type algorithms running on the sensor versus up in the cloud. And there's a lot of discussions around that. I don't know if the technology is quite there yet, but I see that that's definitely the trend.
And John, this is Devin, by the way. Just to add some to that, we talked a little bit about combination sensors and, of course, vibration and temperature, and then, combining other technologies and also adding, some self-diagnostic features, is critical down the road in terms of ensuring that the data that you're getting is, is accurate and there aren't any issues with it. So I think there's some of that, as well as, the 8911 adding some edge intelligence to that. So, a number of different areas where I think things are getting smarter and providing more and more reliable information for the user.
Okay. Another question concerns HVAC application. When you're putting a sensor in an HVAC system, what are the challenges there typically?
I guess I can handle that one a little bit, I guess. It really depends exactly where on the HVAC application. So for, if it's equipment, there are a lot of examples where you have, a lot of freezing and thawing and high vibration and things like that. So you have to be, that can be critical to the application. There are other, applications where you're looking at things like variable air volume, where you need to have, very low pressures that you're able to measure, reliably. So I guess to some extent, it kind of depends exactly, where, whether you're measuring airflow or you're measuring vibration or you're measuring temperature or pressure. So, you really have to look at exactly what it is that you're trying to measure, where you're measuring it, and what the, the actual environment that the sensor itself is going to see. So, it can vary between a board mount or a surface mount sensor to a a ruggedized transducer vibration sensor that's going to see, everything from high vibrations to outdoor environments. So it really varies, but, the important thing is to understand, where it's going to be used and what the environment that it's going to see, so that you can ensure that the sensor is going to be reliable in that type of application.
Got it. Next question. You guys working on TMR magnetic sensors by any chance, particularly for precision sensing? Do you see a role for it?
John, I can take a little bit of a shot at that. The TMR sensor is actually a part of our magnetoresistive product line. There have been recent developments in a technology called tunneling magnetoresistive sensors, and they offer some performance advantages over the traditional magnetoresistive approaches. We are, in fact, looking at that very hard and expect that we will be introducing some products down the road that feature the tunneling magnetoresistive technology. So I really can't reveal much more than that about it, but yes, it's on our radar. We understand how to make it, and keep your eyes out, because we'll be seeing it here at some point in the future.
Cool. Next question is about gas sensors. When you're trying to sense gas, you typically need to measure the temperature and sometimes the humidity. Do you have a multi-sensing device that'll give you this data, or do you have to do it separately?
Well, I can start, and this is Devin. Just in terms of humidity and temperature, we certainly have a number. We have some surface mount sensors that are designed specifically for humidity and temperature sensing in a single product. As terms, I guess combining that with a gas sensing, and maybe Pete, you can provide some more information on this. I think you're a little more closer to that. But we are looking at some flow technology that we have to do some specialized gas sensing. So, certainly we have all of the technologies, and it's a question of combining those three together. So I don't know if you want to add anything to that, Pete.
Just a little bit. As Devin points out, our humidity product line, I think all of the surface mount products there contain a temperature sensor built into it. So with those two sensing capabilities, you can actually calculate a third parameter called dew point, and with a little bit of software. So with a single sensor with two sensing capabilities built into it, we can actually provide three pieces of data that could be interesting to the application. So, and that particular group of sensors are good examples of several products where we're doing multiple sensors in single packages. We call them multi-sensor modules or fusion sensors, or there's a number of names that are used in the industry for that, but they provide multiple sensing capabilities for different parameters in a single package. So it makes it more convenient for the user. They're really only having to mount and deal with one particular sensor, and purchase and stock a single sensor too. So there's logistics advantages to this also. But yes, we do have products that address that issue.
Okay. Next one is another question about cloud data. Sensors that send their data back to the cloud, they can either be wired in or they can do it wirelessly right at the sensor. What percentage of your customers are asking for wireless sensors?
Okay, this is John, and I can take this one. And really today what we're finding is it's application dependent. So in some cases, it makes a lot of sense to go to a wireless sensor because of cost. One good area is like in hazardous locations where you have need ATEX or Class 1 Div 1 or intrinsically safe type of products, because it's very expensive to run cabling. Like in an oil field, they quote $500 a foot type of ranges to run cabling between sensors. So if you are able to have wireless sensors, then that clearly is an advantage out there to go do that. But right now, I think we're getting, and this is anecdotal more than anything, I think we're getting more requests for wireless. and a lot of interest in wireless, but we still see a bulk of our sales and product lines are still in the wired sensors because I see wireless is evolving. And part of that's because of the trends we talked about earlier, and that the low power wireless, the ability to get longer battery life, things like that are really just coming to the forefront, so that we're going to see more and more sensors out there that are going to be able to last 3, 4, 5, 10 years. And then all of a sudden, wires don't make a lot of sense.
Okay. Another one of our listeners wants to know what level of experience does TE have in designing and manufacturing sensors for industrial applications? I get the impression you guys didn't just start doing this last Tuesday.
I don't know, Pete or Devin, you guys want to take that?
Yeah, I can take it. We didn't start last Tuesday. We started a Tuesday probably in 1968 or somewhere. So we've had a tremendous experience. One of the things that TE, not only our sensors group, but our connector group also focuses on are sensors and products that are designed and developed for survival in what we call harsh environments. And typically that relates to the way we package our products. We're very good at packaging products that will last, will have good long-term reliability in very difficult places. As you know, with industrial IoT, people are adding sensors to factories, and in many cases they're putting sensors into places that are not so friendly to sensors in terms of EMI, RFI issues or temperature issues, humidity, contamination, dirt, grease, oil, corrosive materials. And so we pride ourselves in the ability to provide sensors that can survive those kinds of environments. We've made sensors from exotic materials like Hastelloy, Inconel, titanium. We've even got a new temperature sensor that, because of the unusual environment that it's being placed, is gold-plated. So it literally is gold-plated. So we have a long history of doing that and doing it very well. So just so you know, when you come to us, you're going to get a sensor that will last. So back to you.
On a related note, you talk a little bit about intrinsically safe sensors. Where do you need those?
Pete, that's yours. You're the intrinsically safe expert of.
Okay. One part of the industrial world that is adding IoT is the oil and gas industry. And most of the objects or materials that get placed into, for example, an oil refinery or a oil well or a wellhead or oil transportation in pipelines or in trucks or other rail cars have to worry about the possibility of the contents exploding if it finds the wrong conditions, whether it might be a spark or an arc or excessive heat. These can cause serious problems. And what they want to make sure of is that none of the components that come in contact with these combustible materials can start, initiate, or create a hazardous environment where the material might catch fire or explode and cause damage, not only serious damage but injuries to people in the area. And in fact, lately you see some of these explosions where they literally obliterate part of a city. I think one happened in the Middle East here a few months ago. So we do our sensors. We do meet many certifications for intrinsic safety. Most countries have their own sets of regulations and requirements for these kinds of products. They're all quite similar. And so we do get these intrinsic safety certifications from the United States, Canada. European Union has their own set of standards called ATEX. And so, but it ensures that our sensors will not create a hazardous situation if they fail. Many times electronic products fail and you'll get arcs and sparks, and those arcs and sparks can ignite hazardous materials. And so our sensors are designed. It's primarily a packaging effort that's undertaken to provide that kind of capability. So we do have a whole line of intrinsically safe pressure sensors that have been in the market for years and years and years, and we've never had one of them start an explosion. So we feel good about that.
Yeah, I hate explosions myself. I think we got time for one more, guys. Our listeners would like to know if they want to chat with you further. Is there an email address they can use?
There's one that you can use specifically for IoT. It's iotsupport@te.com. You can send an email there. And I think there's also one on our corporate website as well. I honestly don't know what that one is, but we can reply back and let everybody know what that would be. But iotsupport@te.com will get you to for IoT questions.
Okay. And with that, I also want to remind our attendees that they will be getting a link to watch this webinar on demand, and that'll be emailed to them pretty soon. And with that, we're going to conclude things. So guys, thanks for that. Very informative. And for our attendees, have a productive rest of your day.